Hello, my name is Kelvin Tobias, and I'm presenting my software engineering Capstone project, which is the Student Progress Tracker. This is a cross-platform mobile application that solves a real-world problem for all students, such as managing academic terms, calculating weighted GPAs, tracking educational finances, and generating professional reports, all in one unified platform. The tech stack I use is .NET MAUI for the mobile client, in addition to ASP.NET Core Web API for the backend and Azure SQL database for data persistence. The entire application is deployed to Microsoft Azure. I'm going to start by showing you the live API through Swagger, walk through the architecture, then demonstrate all the features in the mobile application. Let's begin. All right, next we'll look at the backend API. This serves as the centralized brain for the entire system. I have deployed this to Azure App Service, ensuring that it is accessible globally and scales according to user demand. The system is organized of 8 RESTful controllers. These aren't just random endpoints. They represent the core business pillars of the application. So for security and access, we have authentication, uh, user authentication and authorization. Academic logic, we have terms, courses. We also have assessments. For our financial intelligence, we have expenses, income, that also assists with student budget management. And for data utility, we have the search reports, which is our our cross-cutting functionality. So this is an example of RESTful API design and a separation of concerns. Each controller handles one specific domain, making the system easy to maintain and testable. In the model layer at the bottom, I utilize inheritance. So every entity, be it a term, a course, or assessment inherits from the base entity class. This allows us to share common properties like IDs and timestamps across the entire system without duplicating any code. Similarly, in our view model layer, every class inherits from the observable object. This is what enables two-way binding, represented by these orange arrows. Child classes, term, course, and assessment inherit shared behavior from the parent class base entity, following the drive principle or don't repeat yourself. Without inheritance, you'd copy and paste the same ID and template into every single model class. In the center of the diagram, you see the view model layer. This acts as a gatekeeper. Here I applied encapsulation to keep the complex logic and private data fields hidden from the view layer. For example, GPA page doesn't need to know the API service talks to the web. It only cares about the final result. By hiding the implementation details, we protect the system from accidental side effects and make the system significantly easier to debug and maintain. This is an example of encapsulation. Finally, the connection between the view models and our service layer demonstrates what is called polymorphism. I used an interface-based approach such as alert service. This means that the view models aren't locked into one specific way of sending notifications. This flexibility allows us to swap our data access methods or notification styles without rewriting the core application. It makes the software more future-proof and allows for unit testing and team collaboration that characterize professional-grade development. This is my example of polymorphism. So to summarize this part of my project, the three object-oriented programming pillars of my project is inheritance with the base entity class. Then we have encapsulation, which is used by the view models, hiding API service complexity, more of a need-to-know basis. And then we have polymorphism using the alert service interface. So it's the same method name, different behaviors depending on the context. So if you notice how I was trying to log in, the indicator while we were authenticating was spinning at the bottom. That was actually working against the API. So behind the scenes, the API is receiving what's called a JWT token that will authorize all subsequent requests. This is an example of token-based authentication, industry standard security where the server issues a token after login and the client includes it with every subsequent request. This is what's called stateless authentication. The server doesn't need to track the sessions. So after authentication, the user lands on the dashboard. This provides an at-a-glance view of their academic status, current term, and upcoming assignments. If you go to term management here, that's where you have your full CRUD functions, which is create, uh, upload, and to delete. I'll demonstrate, okay, here in term management, I'll demonstrate full CRUD lifestyle, cycle, create, read, update, and delete. So here I'll go ahead and edit. I'll delete this term. And then for the sake of the demonstration, I'll create another one. I'll say test term for Panopto. So there I demonstrated full CRUD lifecycle. When I tap the save, the data is sent to the API via the HTTP post request that the UI updates immediately through the data binding. This is an example of input validation and data binding. Client-side validation improves user experience by catching errors early, while two-way binding from the MVVM keeps the UI synchronized with underlying data. And now here you can see the new term appears on our list. This data is persisted to Azure SQL database and retrieved through our terms controller API. This is an example of what's called data persistence. Information survives at restarts because it's stored in a cloud database, not just local memory. If I wanted to update this as well, I can update here and save. Within each term, within each term, students track individual courses. Each course includes status tracking, whether it's the progress, completed, dropped, or plan to take. Course details include the instructor information such as notes, associated assessments. This is a hierarchical relationship. Terms contain courses and courses contain assessments. Mirrors the real world WGU academic structure. This is a This is an example of what's called data modeling. The data structure reflects real-world relationships. Each course can have multiple assessments, objective assessments like exams or performance assessments like projects. Let me show you an example. Save. As you can see, they are displayed here. Assessments track the type, due date, and completion status. This app can also send notification reminders for upcoming due dates. This is an example of notification and user engagement. Proactive reminders help users stay on track without manually checking the app daily. One of the key features is the weighted GPA calculator. This isn't just adding grades and dividing it. It accounts for credit hours, giving appropriate weight to each course. The calculation happens server-side on the API and to ensure consistency, whether you access this from your phone, your tablet, or future web app. The GPA logic is centralized and reliable. This is an example of centralized business logic. Critical calculations live in the API, not on the client. Beyond academics, students need to manage educational expenses. The financial module tracks income sources like financial expenses, tuition, books, and supplies. Users can categorize transactions to see their balance. This helps answer the question, am I on budget for this term? This is an example of feature expansion with domain. The app stays focused on student success, but recognizes finances are a big part of the future. Uh, the report feature generates a comprehensive PDF summary of the student's academic process. This could be shared with advisors, used for scholarship applications, or kept for personal records. This report aggregates data across terms, the courses, the assessments, the finances into one professional document. This demonstrates the system's ability to synthesize information, not just store it. For an example, I'm going to export this to a Word document. Once I exported this to a Word document, this encapsulates my current financial status for the term. Great. For users with multiple terms and dozens of courses, the search feature allows quick lookup across all entities. So I'm going to start by saying the search queries the API, which uses parameterized queries against the database, preventing SQL injection while delivering fast results. So this is an example of security by design. Parameterized queries treat user input as data, not executable code. This is a fundamental security principle. That includes my live demonstration of using complete user journey, authentication, academic tracking through terms, courses, assessments, GPA calculation, financial management, and professional reports generation, all powered by our secure, scalable cloud backend. Uh, this is my example of end-to-end solution delivery. It's not just code, but a working product that solves real-world problems from login to output. Once again, my name is Kelvin R. Tobias, and thank you to WGU, this phenomenal institution, and all my instructors. Take care.